In example 3, it wants us to evaluate these integrals, but it wants us to appeal to geometry. So I need to see what this integrand looks like as a function so that I can in fact appeal to its geometry, see what shapes it makes. And so this integrand makes a function 1 minus x, a y-intercept of 1 and a slope of -1, looks like this. A line drawn in yellow, and of course this is a terrible line, it's all jagged. That is supposed to be straight. I see from this that I've got a 1 area above, and I've got over here a2, an area below, and this integral will equal the a1 minus the a2, which equals 1/2 base times height minus the second one, which is 1/2 base times height. So look at that. The net area, or integral, equals 0. In B, the function is a simple constant horizontal segment from -2 to 4, and that looks like one giant rectangle. So this is the area of the rectangle, and that area is going to be base of 6 times the height of 2, which equals 12. Integral equals 12. Net area equals actual area equals 12. The last part of lesson 1A is a look at some properties. This is pretty intuitive, so I'm just going to get right to it. These properties were given to us, these values rather were given to us, and the first example in this yellow, it wants us to show that we can pull a constant out of the definite integral. So I pull the -2 out. Then I know that the value from 1 to 9 of f of x dx is given here. So that's going to be times a -1, and the answer to that is 2. And the second one, the purpose of this is to show that we can break this integral into the sums, just like we did before with indefinite integrals. And from above, from 7 to 9 of f is the 5, and from 7 to 9 of the h is the 4. Add those together, we get 9. The third one is just a combination, 2 times the integral from 7 to 9 f of x dx minus 3 pulled out of the integral from 7 to 9 h of x dx, and that of course is 2 times -1 minus 3 times 5, which equals -17. This orange one goes back to the thing we did a couple examples ago, where it's going from a large to a small bound, so I can do the opposite of small to large, f of x dx, which is going to be then the opposite of -1, which comes out to be +1. This next one is perhaps the most interesting. The purpose of this particular one is to show that we can break this up to any number here. I put a little box to represent any number as long as the box of the top matches up with the box of the bottom here in this diagonal connection, f of x dx, and put a 7 here. So I am permitted to put any value in that box, and the value I'm going to choose to put in the box is a 9, because that will help me use my properties above. So now the integral from 1 to 9 is equal to, actually let's write it like this. Let's say the integral from 1 to 9 f of x dx, and I'm going to switch this because now the lower bound is on top, so I'm going to make the lower bound on the bottom. So I made it opposite, f of x dx. There we go. Now I like it. So now I have a -1 minus the value of 5, which comes out to be -6. Pretty cool, huh? Last one is going to be the opposite of the integral 7 to 9, h of x minus f of x dx. So minus the integral of 7 to 9, h of x dx, plus the integral from 7 to 9. See, I distributed the negative, And this comes out to be opposite of 4 plus 5 equals 1.